Hello and welcome to this video for Mechanics of Deformable Solids. We are still in chapter 6, torsion. So in the previous chapter, we defined the internal torque, which is going to be the first thing that matters when predicting the deformation and the stress of a beam subjected to a torque. But there is a second thing that is also going to matter, which is the geometry of the torque of the shaft. So in the very same way that when you have an actual load, when you want to calculate its deformation, there are two things that matters. There is first the internal load that the beam is experiencing, and also there is the geometry of the beam. That is to say, in this case, what matters is the area of the cross section. The larger is the area of the cross section, the more the beam will be resistant to elongation. In this case, it's the same thing. So if you take two shafts like this, which have a different geometry, like for example, in one case, you would have a completely full shaft like this, which is filled with solid. In another case, you would have something hollow like this, like some kind of hollow donut shape, so with a hole in the middle. Then in this case, the fact that those two shafts have a different geometry for their cross-section means that they will also have a different deformation. So in this case, in the case of the actual load, what matters for the geometry is the area of the cross-section. In the case of the torsion, the geometrical feature of the beam that will matter is the polar moment of inertia of the cross-section. So that's what we are going to define now. So to define the polar moment of inertia of the cross-section of a given shaft, so let's consider a circular shaft like this. So let's assume that you have a shaft like this, and let's take a cross-section of this shaft. So let's take for a given position X, we take the cross-section, and then we are going to look at what this cross-section looks like if you draw it on a plane. So in this case, so let's assume that this is a circular cross-section. So the cross-section would look like a circle like this. If this is, in this case, the x-axis, so then we can define an axis y that would be like this, and an axis z that would go like this, so that and this would be the axis x like this, so that those three axes are perpendicular to each other, where axis y would be here. And so if I draw now the cross section, then you would have the axis x that is pointing towards you, and axis y going towards the right, axis z going upwards. So now the definition for the polar moment of inertia is going to be as follows. So the polar moment of inertia is going to be the geometrical feature that will control for a given shaft its resistance to a torque. And in this case, the way to define the polar moment of inertia, for this I need to use the cylindric coordinates, which means that if you have a given point M, what I'm going to do to define the position of this point M within this cross section is that I'm going to define this axis that starts from the center of the beam and points towards the point M. And so the first thing is that we have the angle theta here, which is the angle with respect to the y-axis. And then the second thing that we are going to define is the position, the distance of the point M to the center of the beam, which I'm going to write R, the position of the point M, its distance from the center, so that for a given point M, the point M in this cylindric coordinate is defined, the position of this point is defined by its distance R from the center, and the angle theta that the axis, the direction OM makes with respect to the y-axis. And then based on this, I'm going to define the polar moment of inertia, which I'm going to write J as the integral over the surface of the cross section, so the surface A of the cross section, the integral over A of R square dA. So the integral of the square of the distance. So I'm going to do the sum of all the point M belonging to the entire cross-section dA, and I'm going to take the sum over the entire cross-section A of the square R square times the element of surface dA. And that's going to be the definition of the polar moment of inertia. Just out of as a point of comparison, if I wanted to calculate the area of the cross section, would be the integral over the entire cross section A of the surface. If I take the sum of all the small element of infinitesimal surface around each point M, and I take the sum of all those surface along the entire cross section A, then you would get the area. So in this case now, the difference between the area and the polar moment of inertia is that rather than simply summing all the elements of surface, now you are summing the element of surface weighted by the distance to the square from the center. So it's a little bit hard to imagine what the polar moment of inertia mean. And the reason that it's hard is that because of the unit of this polar moment of inertia. If you look at the unit of the polar moment of inertia, it's a square distance times a surface. So the unit of the polar moment of inertia is in meter to the power 4. So it's a little bit hard to understand the meaning of a property that has the unit that is meters to the power 4, because we are not used to understand what this means. So just to give you some intuition about what the polar moment of inertia means, is that if you have a beam with a cross-section that is a small tube that is filled with matter like this, so if you have a beam with a cross-section like this, then when you are summing, you take all the point M belonging to this cylinder, you take their square distance from the center, because here all the point M have a small distance from the center. When you take the sum of all the point M of the square distance from the center, then this is going to give you a low polar moment of inertia. Why? Because on average all the points M are close to the center of those circles. On the other hand, if you have a beam that is like this with a cross section that would be like this, and then the shaft looks like this. Now if you look at what would be the polar moment of inertia of this beam, if you take all the point M within the cross section of this beam, then all those point M have a high distance r from the center of this cross section, which means that in this case, when you calculate the moment of inertia, all the points M over which you are summing to calculate this integral, they all have a high distance r from the center, which means that in this case, even though those two cross sections may have potentially the same area, because this one is a very thin donut like this, in this case, this one would have a much higher polar moment of inertia. Why? Because all the points of the cross-section, all the points M belonging to this cross-section have a high distance r from the center. So this is going to give you a high moment of inertia, since when you calculate the moment of inertia, what matters is the square distance of the points M belonging to this cross-section. So when calculating the polar moment of inertia of a cross-section, there is a special case which can be used quite often, which is the case of when the cross-section is a circle. So when the cross-section is entirely made of a full circle like this with a radius c. So c in this case is going to be the radius of this circle. So in this case, let's calculate what the polar moment of inertia would be for a full circle like this. So we still have to calculate this integral here. In this case, so the infinitesimal surface dA in cylindric coordinates is going to be first a small variation of the r-axis. So in this case, that would be dr, plus a small variation here over the theta axis. So in this case, so you would have dr like this, and then you would have the distance that corresponds to a small variation of the angle delta. And in this case, the small arc, the small portion of the arc corresponding to a small variation from delta, from theta to theta plus d theta, a small variation theta, would correspond to a distance r d theta. So in this case, the infinitesimal surface in cylindric coordinates would be r square not r square d theta, r dr d theta. So in this case, if you want to calculate this integral, so that would be as follows. So we are going to calculate the value of this integral now for a circle. So the definition remains the same. So it's the integral over the cross section of r square and times dA, where in this case dA is r dr d theta. And then the only thing to do now is to calculate this over the entire cross surface. So when you calculate this over the entire cross section, you are going to calculate it over the entire circle, which means that for the point for the angle theta will vary between 0 to 2 pi. So you're going to take all the values of theta between 0 and 2 pi. And r is going to vary between r equals 0 to r equals c, where c is the radius of the circle. And you are going to calculate this for r cube dr d theta. So in this case, you can rewrite this integral by separating the parts that depends on theta and the parts that depends on r. So I can rewrite this as the integral between theta equals 0 to theta equal 2 pi of simply d theta, and this part only depends on theta, and the integral between r equals 0 to r equals c of r cube dr, and again this part only depends on r. So in this case, the integral between 0 to 2 pi of d theta this is simply equal to 2 pi. And the integral of r cube between 0 and c, this is r to the power 4 divided by 4, taken between 0 and c. So in this case, this thing is equal to c to the power 4 divided by 4. So in this case, that means that for a circle, but this formula is only valid for a circle, the polar moment of inertia for a circle would be pi times the radius of the circle to the power 4 divided by 2. So this is the formula of the polar moment of inertia for a circle, simply pi times the radius to the power 4 divided by 2. And so this quantity, this polar moment of inertia, is going to be useful to calculate the deformation and the shear stress within a beam that is subjected to torsion, because it's going to capture the effect of the geometry in the same fashion as the area of the cross section captures the effect of the geometry in the case of axial load.